right. Well, happy Monday. Hopefully you had a good Thanksgiving. Uh, we actually don't. We got a lot this week, but it's not a lot because inheritance and recursion are topics we're going to actually dive deep on next semester if you're continuing on. So we're just going to briefly talk about them here. Um, I didn't bother turning on any of the Xylabs for them. Um, if you want to do them, I can turn them on, or I think I can mark them as optional. But we're going to come back to this next semester, so we don't need to spend a lot of time on it here. The Python for Data Science chapter is really fun. This is cool. So we'll just look really quickly at a couple cool tools, a couple cool libraries. Yeah.
Group massage on the readings, right?
Yeah, so your scores for anything that's not hidden. So it should be all the labs up until then, right? So anything that was not marked as hidden, um, you get your score on. So I can run a report and get your scores for you and like plug in. I think it shows you your scores for it too, right? Your percentage complete. So I'll just take your percentage complete across all of them.
Okay. So it's participation, challenge, out.
Yeah,
Oh,
yeah, the participation, the challenge, and the Xylabs. So most of the points come from Xylabs because it's you get like 10 points per Xylab and like 1 point per participation. So it's weighted heavily towards the labs. But yeah, so I'll run that for you probably like maybe a couple days before the final project so you can see what it is. And then on 12/13, probably at night or something, I'll run the last Xylab report or Xybox report and plug in your scores for it. So you can see what you are. Um, so the Zybooks make up 10%. The labs we've been doing every Monday make up 10%. I got to get you in your scores for that. Sorry. And then the projects you've been self-assessing yourself. So basically, you get your score unless you just completely made it up. Right? If you told me you did everything and you didn't do it all, you don't get the points. But if you told me you did it and it was close, you'll still get the points, right? I'm not expecting it to be perfect, so that's okay. The midterm, I think, was already scored for you, right? You guys did pretty good on that one. And then the final project makes up the bulk of the score that we're working on. Remember, we do need at least 10 commits. So we've got at least 10 days still to work on it here if you haven't started it yet. If you started it over break, great. Hopefully I didn't ruin your break. Sorry. That you still hopefully got a little bit of time off. And then for new stuff, so I can't stay for lab. I'm sorry. I gotta take my daughter to the doctor. The clinic's only open on Mondays for I don't know why. So I'll post a lab assignment. It's just a quick practice using some of the cool tools here. We'll just make a chart, which is really fun. There's a fun little exercise we'll look at. And it won't be on inheritance or recursion because we'll come back to those topics. And then in terms of objectives here, we haven't really done much with UML use case diagrams or activity diagrams. The activity diagrams are sort of like, hey, here's the flow of what happens here, right? Does my program, yes, it does this, or no, it does this, right? Based on my answers. We drew a quick picture. We didn't do the use case diagrams. We'll do that more on Wednesday. We'll look at how we pick which design is better, right? Anything that gets the job done is good, but which is objectively better. So be able to see which is a better solution. Test cases based on pre and post conditions. Some people love this pre and post condition thing. I'm not fond of it here, but we've done some testing. Right? And the idea is what is true before my code runs and what is true after my code runs. It's just a fancy term for that. So precondition is what's true before, post condition is what's true after. That's like our assert. So after it's done, we're asserting this is the given case here. The precondition is like you can't call this function unless you have a value or some silly stuff like that. Not too big of a deal. We'll decompose a complicated problem into simpler subproblems. We'll do functional decomposition. This is my favorite technical term. Hopefully, you threw it out there at your Thanksgiving dinner and everyone looks at you like you're crazy. It's fun. You'll love that look. And eventually, they'll ask you to fix their printer. You're like, no, I'm not. I'm a computer scientist or data scientist. I'm not a computer printer technician, but I still can fix your printer. That's okay because you know how to Google. We'll process programs using our integrated programming environment. Again, I'm fond of PyCharm. You can use lots of different ones here. We'll systematically test and debug small programs, right? We'll build them, run them, test them, make sure they work. We'll trace algorithms for correctness using simple test cases. That's our test cases. Right? Does it work? Does my algorithm do what it's supposed to do? We'll do something like Visio to draw UML activity diagrams. We'll use a website because it's much easier. I'll show you a free website. We use our symbolic debugger to assist in the process of identifying and removing defects from buggy algorithms. We'll use the debugger. Right, we've done that. Pre and post conditions as part of the process of documenting software modules. I'm just gonna not do this one here. Sorry, my apologies. It is an outcome. I just don't care. Forgive me. I should care more. Um, if you can write a code comment, you can do this. Right? It's not worth our time. I promise you, it's not worth your time. Uh, but I assume if you know how to write a code comment, you could do this if you wanted to. I'm just not going to ask you to. We'll write a recursive procedure. We'll do it today. It's okay. It's really quick. We'll do it again next semester more. We'll talk about what that means. Write a small program to solve a data science problem. Again, it's a bit of a stretch here. Our little Monopoly game. The next step would be automating this, being able to run it lots of times and do simulations and say, what is the best or the square that's most landed on? Once we have the basic game set up, we can like travel around the board, and then you add in the chance and community chess cards, which will send you to specific squares. You can find out the most popular square to land on is St. James Place on the orange. Right, it's 12 squares after the start here, and one of the chance cards takes you right to that square in St. James Place. That is the most popular square, not by much, but it's the most popular square to land on. But we could do that if we took it one step further. So we're close. Again, it's a bit of a stretch to say we're going to solve a data science problem in our very first class learning how to program, but we're going to simulate things and look at how we can use code to find out things. And again, it's very difficult to mathematically solve some problems in real life because the math gets very messy very quickly. So if we can write a simulation that is close to what happens in real life, we can just do the simulation a gazillion times and see what happens with our simulation. That's one of the advantages of having code, right? I can just try it a bunch of times and see what happens, given all these various inputs and outputs, and I can tweak things and change things. Like accounting for weather is difficult, right? If you wanted to do things for anything, right? Um, like trying to find out what is the most popular day to eat food at a takeout place really depends on the weather, right? If the weather's bad, people aren't going to go out as much. Like it's a weird factor. So it just goes those sort of weird things. And then we'll design and implement functions with versatile behavior, use loops to perform repeated but not independent tasks, and model and process data items with multiple values. It's using our classes, really. Um, so those are all the course objectives that we pretty much have tackled by the end of this week. Believe it or not, we're at the end of our new material, Inheritance, Recursion, Python for Data Science. I missed chapter 15 here, sorry, 13, 14, and 15. Right, we're doing all three. So and again, we'll come back to 13 and 14 essentially next semester, and then 15 is just really fun. So a real quick dive into, yeah,
So just to make sure we're going over something 15 this week.
to 13, 14, and 15. Yep. So just go through and read these ones, do the challenges, but no labs for these ones here, because we'll come back to these topics later. But this is a pretty quick one here. So we fire up PyCharm. So the idea with inheritance is it allows us to, again, sort of model these things in real life that we see, and use less code. So some things in real life have this sort of inherited behavior where when we classify things, if you've taken biology before, remember we have this series of classifications. There's kingdom, phylum, class, order, family, genus, species. I don't know why that's in my head, but it's been there since high school. I can't get it out of my head. So this is, I don't know what I call it, inheritance. Sure. Oh, I forgot to give it a week. Sorry, that'll be okay, or a chapter. So with inheritance, it allows us to be a type of our shared type here, right? So like all mammals share characteristics of mammals, right? We're all warm-blooded. We have hair, give live birth to young. I don't remember what else mammals have in common, but that's close, right? So all mammals have that. But what makes humans different than dogs, right? Is we have different sets of characteristics, but all humans have the same characteristics and all dogs have the same characteristics. So what inheritance lets us do is create that super type here, where we call it the super class that all things can inherit from. So I might have a class like mammal, right? And that class for mammal might have an init here, and then mammal might have self dot name. Right? We have some sort of name here, or we have self dot weight in kilograms or something like that. I don't know for now. And we can take those as arguments if we wanted. Name and weight in kilograms. And then we can set those values here, right? So we got a name, we got a weight, right? And then anything mammals want to do, right? We could add public functions here. And then if we wanted to make a class that is a mammal, but it's a special version of mammal, right? This idea that we're going to inherit from mammal. We are a mammal, but we're special, right? Humans are different than other mammals with certain things here. So we can write a class called human that extends mammal. So with this set of parentheses here, we're inheriting from mammal. We are a mammal. We have all the attributes of mammal. So I can say in my init here, maybe I have, I don't know, what do we want to add? Like eye color, I don't know. Other mammals have eye color. What do we have that's different here? I'm really bad at biology. I shouldn't have picked a biology example. Okay, let's change it here. Let's not do biology because I get confused really easy. Let's go to how about rectangle, right? Define init. We'll have a length and a width. Okay, this is a little easier. We'll say self.length. Oops, if you spell that right, length, the length, and self.width is the width. TH. I can't. I spelled it wrong twice, right? And then things like rectangle now, we can figure out the area. So get area can return self.length times the self.width, right? And we can get perimeter, parameter, that looks right, returns self.length times 2 plus self.width times 2, right? So we can get the area, we can get the perimeter. That works out pretty well. You can add in your parentheses if you want. Um, Probably should mark these as private and say, hey, don't change these directly here because that would be a bad habit here. So we can go fix those here. And then we should put some sanity checking around this, right? The idea with writing a class, right? We're encapsulating all those details. So I'm going to have a set length that takes the length here, right? And then we'll say maybe if my length is greater than 0, then we can say self.length equals the length. Right? Make sure it's good. If not, maybe we just otherwise we'll say self.length. Oops, self.length is 0, right? And we'll do the same for set width, right? We want to sanity check these values. We're protecting the integrity of our class here. Let's replace all these with width here. Now, gotta be careful when you copy paste because it's really easy to screw things up. Like missing my underscores there. That'd have been bad. So self-length and self-width, and then I might as well call them. So self.setLength, given the length, and self.setWidth, because I don't want to do the same work twice here, right? We'll sanity check twice in my init. So here's rectangle, right? Now we're making sure we get at least 0 or more. I guess you can have a 0 length or 0 width, sure. We can get area, we can get perimeter. That's a rectangle, right? Now, back to geometry here. I'm a little bit better with geometry. We can write a class for square, right? All squares are rectangles, right? Right? But not all rectangles are squares. So to init a square, all we need is a size, right? And we can call self.setLength given the size. We call self.setWidth given the size, right? Oops, we're missing something though. It says, what are we missing? We need to call our superclass. So because rectangle has an init that requires a length and width, if we are a rectangle, we also have to call an init that has a length and width. So it's suggesting it for us here, which is really nice. So we want to do our superclass call. If we just say, hey, super init, my superclass, call the init method there. Right? We are a rectangle, so we go to the rectangle init, given length and width. Right? And really, we don't need length and width here. We just need size, and we'll give it size twice. Right? We'll give it size and size. The other thing we can do now is we want to have special behavior. Right? What's different about a square that is not common to a rectangle? Well, squares need to make sure that they have the same length and width. So I'm going to add a new method for set length here that takes a length. Yeah.
What is the super length?
So super says go to your super class, the class that you are inheriting from. So in this case, I am a rectangle. So I put rectangle in parentheses here. I am a rectangle, but I'm a special version of rectangle.
So super will be rectangle.
Yeah, so super is rectangle. Yep. Yep. So set length, we want to do something different for set length. We don't want this set length to work here because then we're going to be not a square. Right? If you can change the length separately from the width, you're no longer a square. So to protect the integrity of our class, our sanity check here is we want super dot set length or set width to length and super dot set length to length. There you go. So if you try and change the length of a square, we want both the length and width of the rectangle class to change because squares need to make sure they stay square, right? We want to do the same thing with set width. So if you give me a width here, I'll also then change the length and the width to the same width. So this makes sure that I stay a square, right? You should not be able to change a square's length and width independently. This ties them together because we're a special version of rectangle. because we are a square. We need to stay a square. Now, what's cool is I don't need to rewrite area and perimeter. These functions still are the same for me. So if I want to make a square, yeah.
What is the difference between this three instance and instance rectangle for three?
So I could do that, but so if I with my code, if I have here's a small square, if I say it equals a rectangle, I can give it like 10 and 10, but in the rectangle class, I can call set length, set width to 20. If it's a rectangle, when I set width, the width goes to 20, but the length stays at 10. I'm no longer actually a square, even though my code, I'm telling it it should be a square. It's allowed to do a bad thing, right? So I'm still a rectangle, but I'm no longer a square at this point, and that's oops, no longer a square. Right? So having a class here that is a type of square lets us make sure we behave the way a square should behave. Right? Our code can model that behavior. That squares need to have the same length and width. Right? And then I don't want to have to rewrite get area and get perimeter. So I can make an actual square equal to square, right? And square, then I can say, hey, it's a size 10. And then actual square dot, I have all of these methods here for get perimeter and get area. I should probably add get length and get width too, but that's fine. Right? So I can get the area out and do something with it. And this will not call the square. There is no function in square called get area. The function is in the superclass rectangle get area. So if you are a type of your parent class or superclass or base class, they use three different words for it. I don't know why. You get all of their functions. And that's actually what we did when we did our testing, right? We opened up, I'll just open it here. When we had our testing projects, right, we looked at test examples. Let me do a new window here, right? The tests were of test case. They're a type of test case. They inherited from test case. That's why we had these assert equal methods, functions, right? We didn't write self.assert equals. We have no idea what this is. It comes from the test case class. So because we inherit from test case, we can do all these things that are out of the box ready for us to do. We're just being a special version of that test case because we're testing specifically our bounded value class. That's one of the nice things of inheritance, right? A bunch of work has already been done. I don't need to redo any of that work. I'm just going to take advantage of it and be a special version of it.
All right, where's the super map?
So super just says go to your super class. So like with super.setWidth, it says go to the setWidth class, go to your super class, call setWidth. If I just said setWidth here, setWidth will call setWidth, which calls setWidth, which calls setWidth, which calls setWidth, which I'd have an infinite loop here because I'm calling myself. So I have to have the superclass version of it here, right? If I had this dots, or no, yeah, this dot set width, right? Or no, sorry, self dot set width would call self dot set width, which calls self dot set. So we'd have the bad loop here. So super says go to my superclass's version of set width, which sets the width here. So this makes sure that it stays a square, right? So this ensures it stays square, right? That sort of idea. So we'll get more into this next semester, but we use inheritance. We were using it before with our test cases without even really knowing it, right? There's code already written. We're just going to be a special version of that code, right? That's what it lets us do. So it's lots of fun. You can do things like have your items and have a list of items in a shopping cart. And then now all of a sudden the state of Michigan says, hey, we want to tax you. We want to add a sales tax. Now some items are taxable, but not all items are taxable because we don't want to tax food products. Well, we do want to tax food products, but not fresh food products. So fresh food products are not taxable, but non-fresh food or prepared food products are taxable in addition to other goods sold at stores, but not tampons and pads because we don't want to tax those. So our tax laws are crazy and our computers have to deal with it, right? They have to know, is this item taxable or not taxable? To distinguish between the two. They're still all items. They still have the barcode, they still have the name, they still have the price, they still have the quantity, right? We don't want to reinvent any of that wheel, but for items that are taxable, we want to add in the tax because the state of Michigan wants their cut, right? You have to pay taxes with money that you earned that you've already paid income tax on to the state of Michigan and to the feds, right? It's okay. So that's a big story there. Don't get me started. I'm sorry. Um, so we can take advantage of code that's already written, right? The goal is we don't want to have the same code twice. So if it fits, inheritance is a solution. We don't do it everywhere. Right? It's not a everything solution, but it's a this works very well for specific cases where it makes sense to have inheritance. Okay? And we'll look at some of those cases later on next semester. Like, yes, it's good for these, but we're not going to use it every single time. So inheritance here is one of the ideas of object-oriented programming. It's one of the fundamentals of object-oriented programming that we can inherit from the classes we already wrote here. And this superclass thing is really cool. Uh, so Python doesn't really do this the same way other languages do, but all squares are rectangles, so we can treat them all as rectangles. Yeah.
Square essentially to use the exact same methods as we are defined in the superclass within other class.
You can use those versions and then you can change them if you want. So if you want a different behavior on set width, I can change the behavior of set width. It's called overriding. So I get this little O here. I'm overriding the behavior of my parent class because I want to do something special. If I don't, if I just want get area and get perimeter, I just leave them alone and I get them because I inherit from them. So I get all the things they do, and then I can be special. I can add attributes, I can add functions, I can change function behavior, right? But I get all of the stuff from my other class. Right? And you can inherit from classes that inherit from classes that inherit from classes that inherit from classes that inherit from you can go nuts with this, right? You could make a base class for polygon, and rectangle is a polygon, right? We could do that, right? We could say, hey, I want a class for polygon, uh, right? And then we define an init here. So polygon needs to know the number of sides, right? Right. So self dot, I don't know, side lengths or something, right? Lengths equals a list here, probably, right? And then for side in range number of sides, we'll take our self.side lengths of the side, and we'll say it starts at 0, right, for now. And then maybe we have a set side length that takes a side index and then the length maybe, right? And says, hey, let's take my self.side lengths at side index, set it to the length. Again, probably do some bounds checking, make sure it's more than 0, but that's fine here, right? That's all good here. Now a polygon, we don't have no idea what area is, but we can get perimeter, right? Of a polygon, we just return the sum of self.side lengths. It's pretty easy to get the perimeter, right, of a polygon. I don't even know if it's closed or not, so this may or may not be good geometry here, but right, rectangle then is a polygon, right? And maybe you need a way to like get side length, given a side index. You can return self dot side lengths of the side index. Sure. So for a kind of polygon then, well, I know that I have 4 sides. So I can call super.init and I can say I have 4 sides. And now I'm not going to set length and set, I guess I can set length and set width here. So if I have 4 sides, I don't have length, I don't need a length and width property anymore. I can say self.set side length of 0 in length, right? So index 0 is the first one, and the matching one then will be index 2. So 0 and 2 are length, right? Here, let's change it. So you can, if you like less indenting here, we can do the opposite here. We can say if length is less than 0, length equals 0. And then we can just do this code here. Some people find this a little prettier, and then I'm gonna have to type a lot less, right? So change what I'm setting length. So if it's less than 0, set it to 0. And then no matter what, I can do this. Okay. And again, if you're thinking about unit tests, right? Now, one test here will cover all my code. I don't need to have a test for an if and a test for an else. Right? So it also saves me a little bit of time testing later. I don't need to test the if case and test the else case. I just need to test this one here, right? Because I know that it's going to work. Set width is the same thing here, right? But now it's width for sides 1 and 3, right? And then maybe we have a get length, define get length, return self.get side length of index 0, right? And how about a get width of index 1, right? Now my rectangle is a polygon, right? Great, we're happy here. And now square is a rectangle, which is a polygon. Oh, I can't do self length here, so I can do self.get length and self.get width. And now I don't need to redo perimeter, right? My perimeter is already done for me. It's already going to sum that, right? I don't have to do my own arithmetic for it, which is nice. So that's all. So you can make this chain of inheritance as far as you want to go, right? At some point, it stops making sense, but you can have classes that inherit from classes that inherit from classes that inherit. And next semester, when you start looking at some basic data structures, they do that. We use inheritance up to the wazoo because we don't want to reinvent the wheel here for different types. Okay, so it gives you some tools. It's kind of fun. It gives you a lot of tools. So it is a relationship, right? A square is a rectangle, not a has a, right? Where like gradebook has a student, gradebook is not a student, and student is not a gradebook, right? Student has an assignment, right? So classes can have instances of others. They don't have to be is that kind. So a lot of students, when you're first learning out, you're like, inheritance is awesome. Everything should inherit. And you're like, student is a gradebook. And it really doesn't make any sense there. So you got to kind of like pause and think about what that relationship looks like.
What about in what assignment is in completion in class?
Yeah. So student has a assignment or has assignments. Right? You can have a bunch of those classes as attributes, and you're not is. Right? Assignment is not a student. Student is not an assignment. It only makes sense for those relationships. Yeah. Yep. Yeah. So the has a is much more common, but sometimes this is a relationship is fantastic. And then we did unit tests. We kind of jumped ahead here. Uh, Python lets you do multiple inheritance, and this idea of this mix in here. So like vampire bats are mammals and winged animals. Right? All winged animals can flap their wings and they have a wingspan. All mammals can breathe and give birth. So vampire bats, if they inherit from both, get all the functions. Super fun. Most languages don't let you do this. Python does, because Python's fun like that. They're like, hey, you want to be lots of types? Go for it. It gets to be a little weird when you have like multiple classes with the same function. Then it gets messy because like the first one that finds a match in the order that you name them is what it's going to be. But like a flying car could have a transport mode, it could be a flying mix and have a driving mix in because when you fly, you can fly, you can roll, you can eject. When you drive, you change tire, you check oil, sure. And then transport to do like, they can go and do things, right? A semi truck is a transport mode that drives, a flying car is a transport mode that flies and drives. Sure. So you can go nuts with these things. So that's a quick intro to inheritance. Um, let's look at, oh my goodness, recursion. Just a quick intro to recursion. We close, do a new project here. Let's do recursion. So recursion is actually really, really easy, but doing it right is hard. So the quick definition here. So do you guys remember Fibonacci? The Fibonacci sequence? That you have like the nth value of the Fibonacci sequence have a given value. Do you remember that? Remember the mathematical definition? So we're going to return Fibonacci of nth minus 1 plus Fibonacci of nth minus 2. That's the literal definition of Fibonacci, right? This function will call itself and call itself and call itself, but oh, we missed something here. If my n is equal to, or let's say maybe less than 2, return a 1. Now, some people in math land tell me Fibonacci starts with 0. Other times it looks like it starts with 1. I prefer that it starts with 1 because otherwise it doesn't make sense to me, but that's okay. So I'm going to say the nth value, so the first Fibonacci number we'll say is 1. The second Fibonacci number we'll say is 1. Other than that, I need to take n minus 1 and n minus 2. Nth minus 1, nth minus 2, right? That's the definition of Fibonacci, right? Do you hear about the Fibonacci party they're throwing? I hear it's going to be as big as the last two combined. The Fibonacci party they're throwing, they'll be as big as the last two combined. Yeah, I love math jokes. Yeah, that's me. That's okay. All right, so this is Fibonacci, right? So we can say for, I don't know, nth in range, let's do like 40 or so. We'll print nth and Fibonacci of nth, right? Maybe a colon, right? How about that? We'll colon separate them here. Give this a run, and I'll get the first 40 Fibonacci numbers. It's a little slow, though. My goodness. Come on, computer. Go faster. Uh-oh. 38. 39. Okay, we got to 39. So, what is that? 63 million or so. And notice how slow that was going? Now, this is recursion. This function calls itself. That's all recursion is. A function that calls itself is recursion. Because Fibonacci calls Fibonacci. It calls Fibonacci. It calls Fibonacci. It calls Fibonacci. It calls. Eventually, we'll get back something that does not call Fibonacci. This is known as the base case. If you know the solution, you're done recursion. You're done with recursion. I've solved it. If I don't know the answer, I need to recurse more. So the idea with recursion is if you have a complex problem that you can simplify, take one step closer to a known solution, it might be solvable with recursion. This idea, if you can identify the base case and you can take a complex problem and break it down, make it one step simpler, you might be able to solve it with recursion. Again, we'll come back to this next semester. We'll do a lot more with it. But turns out this is really, really, really dumb here because what I've done is added up the number one 63 million times to get Fibonacci of 39, right? This is a terrible way to do this, right? So recursion here doesn't always make a good solution, right? It's actually really easy here. So we'll say better fib here of an nth is we just make a loop. We have the previous is 1, we have the current is 1, and we have a current nth is 3, I guess, right? And I guess really we kind of this first one here, if nth is, we'll do this here, right? And then while my current nth is less than the nth I want, right? As long as we're less than, we'll say my next is equal to my previous plus my current. My previous equals the current, and my current equals the next. And then I should take current nth plus equals 1, right? Set the next value, set previous to current, set current to next. When I'm done, I can return the current, right? Actually, no. So if current is 2 here. So we started at 2, right? Because if I want the third, 2 is less than 3. Next will be 1 plus 1. My current will be the next, it'll be 2, and I can return the current. So I should be in good shape here. So this one, better fib, is infinitely faster. Maybe not infinitely, that's the wrong term here, but it's so much faster here. So you don't even see it run because Python can do this fast. Adding up 63 million ones is really, 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 really slow, right? Exponentially slower. Exponentially is the right word here, not infinite, exponentially slower. So you just got to be careful with recursion. So we'll come back to it later here. Lots of silly things we can do with recursion, lots of really fun things we can do with recursion. If you ever had trouble solving Sudoku, you can solve a Sudoku puzzle very easily with recursion, right? You remember Sudoku puzzles? They have the numbers 1 through 9 in the grid, in the row, in the column. So turns out if you can do things really, really, really fast, you just pick the first number that fits in the top left square and then see if you can solve the puzzle. If it doesn't work, try the next number. Eventually, you'll find a number that does work, right? So if you look at a Sudoku puzzle, right? So let's look at one of these ones here. Here we go. So you find the first open square and say, okay, let's put a 1 here. Great, I can put a 1 here. It's not in the row, it's not in the column, it's not in my box. Great. Go to the next square. Can I put a 1 here? No, because there's a 1 in the row. Can I put a 2 here? Sure, there's no 2 in the rows, no 2 in the column, no 2 in the box. Put a 2 here. Go to the next open square. Can I put a 3 here? No, because there's a 3 in the row. Can I put a 4 here? Sure, put a 4 here. Right? Eventually, like, okay, come here. I can't put a 5. Can I put a 6? Can't put a 6. Can I put a 7? I can't put a 7. Can I put an 8? I can put an 8 here. Great. Go to the next row. Can I put a 1, a 2, a 3, a 4, 5, 6, 7, 8? I can put a 9 here. I go to the last square. I can't fit anything here, right? Because I've used up all my other numbers. So now what you have to do is you have to go back and say, okay, well, this number didn't work. Try the next one. Well, 9 didn't work. Okay, go back here. Fix this one. Well, this one was a 7 or an 8, right? That one didn't work. Try a 9 here. So you just try everything. And because your computer can do it really, 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 really fast, you'll solve Sudoku. My wife doesn't think this counts when we play Sudoku together and like see who can beat each other, solve it faster. I can't use my computer program even though I wrote it myself. She said that doesn't count. I said, well, I solved it myself, but apparently using the computer is cheating. So you can do stuff like that. It's called backtracking, right? We're going to try something. If it doesn't work, we'll go back. We'll try something. If it doesn't work, we'll go back. We'll try something. If it doesn't work, we go back.
So Python allows for doing it automatically.
What?
Python can do it automatically.
Why can't it? Why can't it?
Can't do it.
So because eventually a number 1 through 9 will fit here, I will find a solution. I'm just trying every single possible solution on the way there, right? But to do that on paper is really, really, really slow because there's a lot of squares here, a lot of numbers 1 through 9. The computer can do it like that, though. So next semester we'll build a Sudoku solver for fun because it's easy. You can also solve mazes, right? The idea with the maze if you just kind of break it down into a grid here, so maze by grid, essentially, mazegenerator.net, thank you, generate. So like if you imagine each of these as like a square in a two-dimensional array, right? I'm going to start here and I have to end down here. If I'm not at the end, right, my base case is I'm at the end, or my base case is that I got stuck. I'm going to try. So the solution here is you just try up, down, left, right. If you can't go up, you try down. If you can't go down, you try left. If you can't go left, you try right. If you can't go up, down, left, or right, you reach the dead end, go back a square, right? So from here, I try up, down, left, right. Okay, I'm going to go down. I'm going to try up, down, left, right. I already went up, right? Don't step on the same square twice, so go down. Try up, down, left, right. Okay, go right. Eventually, you will find a solution here. It's not a good, efficient maze solver. It's actually one of the worst ones, but it will solve the maze for you with backtracking recursion, right? So the Hansel and Gretel breadcrumbs, right? Leave some breadcrumbs on your path. You'll find out when you hit your path again, find your way home. We'll find our way to the end, essentially. So you can do that, which is really fun. So recursion works really well for some problems, not well for other problems. But sometimes they're good here. So they give you the Fibonacci one here. Patterns and other things are really fun. You can do cool things with recursion. All right, we'll come back to it later. So I figure you can write these. A super easy one too is like countdown, given a number, right? And we can say, hey, if the number is greater than 0, let's print the number, and then we'll call countdown given the number -1, right? Else, if it is 0, we'll print blast off, right? So I can say, hey, let's count down from 10. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. So eventually I will approach the base case, right? I'll get closer and closer and closer to something where I know what the solution is, right? So if we print blast off, we'll just call blast off, or no, countdown, right, of 10, we'll get blast off. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Right? That's very simple recursion. Now, most of these are just loops, right? You don't need anything with recursion here because it's just a loop. Now, there are some cases here, the Tower of Hanoi animated solution here. The Towers of Hanoi is this really cool puzzle here that says, hey, I want 3 pegs here. So get the solution. So if you have 3 pegs, the idea here is you can't put a smaller disk on top of a larger disk. I'm sorry, you can't put a larger disk on top of a smaller disk because it'll crush it. But I have to move all the disks from this peg to this peg. So to do it, well, it's hard to move 7 disks, right? But I can move 6 disks. That's a lot easier, right? Well, it's hard to move six disks, but it's really easy to move 5 disks. Well, I can't do 5, but I can do 4. Well, I can't do 4. Let's do 3. I can't do 3. I can't do 2. Let's do 1. I can move 1 disk. When I'm done moving 1 disk, then I move the second disk to where I wanted it to go and put the first disk back on top. To move the third disk, I move the first 2 off, put the third one where I want, move the second 2 on. Well, moving 2 was hard, right? But I can move 1. So if I show the solution here, actually, let me do the speed factor of like 5. That's too fast. Let's do 3, 2. So it moves 1 disk, moves the second one, moves 1 on top. So to move the third, we move 3, and then repeat from 2, which is 1 and then 2. To move the fourth disk, we move the 3 back onto 4, right? To repeat that process of moving 2, moving 3, moving 1. So it's to move 7, it's move 6. To move 6, it's 5. To move 5, it's 4. 4 is 3. 3 is 2. 2 is 1. To move 2, you repeat the 1. To move 3, you do 2 and then 1, right? You just keep on repeating. This is much easier with recursion, right? The solution here, so recursive solution to Tower Hanoi Python. These are out here. It takes 4 lines of code. That's it. Right? All of that entire thing is just 4 lines of code. Because if your n is 1, you move 1 disk. If it's not 1, take n minus 1 and you just swap the holding disk, the extra peg, right? Because it's let's move 4, but swap destinations, and then I'll move the 5th one, right? Move the last one, and then repeat again. That's all it is. So it's beautiful. You can move all the disks really easily. So recursion is very powerful. So doing this with a loop is much harder, right? Because you have to track all these things, and if you don't know what the size is, it's really hard. So imagine your computer and your file system, right? We open up our projects here all the time. We say, hey, let me go see where this is. So I open in, oh my goodness, open in Explorer. Now, how would I go and find all the files in a folder if there are also folders inside that folder, inside that folder, inside that folder, inside that folder, right? How would I do that? Well, we can use recursion. We can say, hey, if you find a folder, repeat the process of finding all the files. And if you find a folder, find all the files in it. Repeat the process. So recursion works really well for stuff like the file system because I don't know how many folders there are, right? It's open-ended. So I just keep on repeating until I run out of folders. So there's some really good problems we can solve with recursion. We'll get into that later. So that's what recursion is. It's functions that call itself. Okay? All right, now we'll get to the fun stuff. Python for data science. Lots of really cool libraries. So the idea with data science here, um, I actually like the try version of this. I'm not a fan of the second one. I think I've showed you that try one before, right? Data science, Venn diagram. I can't spell. Venn diagram. There we go. Yes, I think it's one of these ones here. This one. So computer science, math and stats, and business and domain knowledge. This is the one I prefer. So we know a little bit of computer science. If you know a little bit of math and stats, you can do machine learning. Right? We can write machine learning algorithms. If you add in your business and domain expertise, now you can do data science because you can interpret the data. You can train your machine learning models because you know what they mean. That's why in the data science program, you take a core set of classes in a particular domain, right? So that you know a lot about that domain, so you understand what we're doing with that data. If you have the math and stats and you have the business domain experience, you can do data analysis. You can crunch the numbers, but without the computer science background, you can't do the machine learning stuff. Computer science and business domain expertise, you get software, right? We get software to solve business problems, right? You combine all three of those, we get the data science trifecta in the center here. I like this diagram, right? Because I can do all of these things and actually get value out of the data. That's the big thing here, right? Just having data is not worth anything. Being able to get information out of your data, that's where it's worthwhile, right? I can look at all the numbers and understand what it means when I do my machine learning algorithms and I analyze the data and I build these trends and forecasts and I can do cool stuff, right? That's the goal there. Yeah.
What's it called? Sure. Right. Sure. Are the basis or when you mentioned learning?
So this is all computer science basics. So we're taking computer science one, computer science two. We teach it in Python for data science students. So there's the fundamentals of computer science. Later, you'll get some of the math and stats in your math and stats courses, and then you'll get your business domain expertise from your focus area, right? Eventually, we'll look at the specific machine learning models and data science models and cool tools we have to do data analysis, machine learning, those sort of things to turn it into data science. We're just still very back in the basics of here's how you make computers go beep boop bop, right?
When these was essentially how about getting
Yeah, yeah. To use all the cool models, we write Python code. So you have to understand how Python code works and how you call functions and those sorts of things to be able to use the cool stuff. Yep, that's why we do. That's why we have the basics. Yep. Um, so there's our fun stuff here. Goodness gracious, there's too many things. The data science life cycle: you gather data, you clean the data, you explore the data, you model the data, you interpret the data. I love this. It's called data wrangling. It's actually a technical term. I had someone challenge me on it. It was like when you're coming up with like program outcomes, that like it goes through this whole border review. They're like, you don't mean data wrangling, right? That's not a real thing. I'm like, oh no, it's a real thing. Google it. It's just funny because it sounds so funny. Like you're gonna go wrangle some cows. You also wrangle data. I enjoy it. So do all that fun stuff here. Look at your data. It's a whole process. All right, Python for data science. So what we want here, why we like Python for data science, is Python's really easy. It's very readable. It's very popular, and people use it. Right. The downside, Python's not quite as fast. That's okay. Not the end of the world. It uses a little bit more memory. It's okay. Memory is relatively cheap in terms of what we have to spend money on. And then all sorts of different libraries are written by all sorts of different people. It's not very consistent. Yeah, that's okay. It's not the end of the world. So Python's great. Other people do stuff with other languages, and that's okay, right? This is one tool in our toolbox. So some of the packages we're going to use. So right now we've only done stuff with Python that's been built in, right? The Python libraries. Now we're going to look at libraries that other people wrote, and they said you can use for free. And these people are amazing. I love these people. Like they write this super cool stuff, and they say you can have it for free. It's an amazing industry because they're like, I want other people to use this because it's so good. And you're like, yes, yes, it is. So NumPy is all sorts of numerical computation stuff. NumPy's used in most every other data science package. Pandas is dealing with tabular and time series data. Pandas is super popular as well. We'll take a quick look at that. We're not going to use it much in one of your labs, you'll use pandas. So it's got built-in functions. Like if you take a look at pandas here, here's their documentation. Let's do like getting started here. So you can,
Select or something.
yeah, yeah, this is the library. So how do we create columns? I don't know, like here's a little tutorial. So you can read a CSV, you can get the header column out, and then you can print it all out. I don't know. You do fun stuff here. So it gives you like example code. People use this all the time. It's amazing. Lots of great stuff we can do with it. So all the libraries have websites that tell you what they can do. Matplotlib is for drawing pictures to do math plots. I love this library. This is one of my favorites here because I like visualizations. Uh, so reference here is, no, we don't want reference. I want documentation. Where is it here? Shoot. Plotting methods. Oh, this is not the one I wanted here. This gives me lots of, is it tutorials? There we go. Plot tutorials. So if you want a plot here, you can go and find the particular plot you want, and they'll give you an example here. So you want to find whatever this kind of plot is here. We can do this plot, a scatter plot, right? We can do line charts, we can do bar charts, anything you want here, they'll have examples for how you want to do it here, which is super cool. Um, we're just looking at it briefly here. So all sorts of fun examples they've got in here. You can do multiple graphs side by side by side. Um, you can render anything you can think of. You can go down and they'll give you like the source code you can go and play with and run, which is super fun. Um, so a pretty quick example, we'll do a matplotlib, we'll do a little graph here, and that'll be our lab exercise. But other cool ones here you can use. So sklearn is super popular for machine learning. There's a bunch of built-in algorithms that let us process our data, fit models, do validation, those sorts of things. This is really popular for building stuff out. If you looked at YouTube videos, they probably use sklearn. All right, lots of fun stuff. Jupyter Notebooks is a super popular integrated development environment. I like PyCharm because the debugging is fantastic in it. You can debug in Jupyter Notebooks. I don't think it's quite as nice, and I like the PyCharm. It does a lot of like autocomplete features for us, which is really pretty. Um, but it lets you kind of mix and match code and text, which is fun. So a lot of people have Jupyter Notebooks built into their Python code that you can go through and look at. So this PY4E Dr. Chuck out at Ann Arbor, the School of Information, has this here, and he's got, where is it here? We want our Jupyter Notebooks from LibreText. So in his book here, like you can go through, here's the chapter on strings. Uh, let's do like string slices. So this is a Jupyter Notebook. It's got text integrated with bits of code here. Oh, this one's not runnable. Hang on, there's places that it's actually runnable. I don't remember where he has it in here. Oh, goodness. Somewhere in here we get runnable bits here. I'm not sure where it is right now, but these like sections here, if we opened up as the Jupyter notebook, you could actually click run on, and you can run one small section at a time, which is really cool. Why is that one not in here? Is it, maybe it's like this one here.
Well, we were actually coding and developing software. Do you use Jupyter Notebooks?
Yeah, Jupyter notebooks are really popular for doing things like that. Here we go. So like you essentially get like here's a place you can run code. This is slightly different, but the idea is like you get text and then you get code you can run. So people will publish their Jupyter notebooks. So you can go and download their examples and actually run the code right there. So you can kind of recreate it very easily of what they're going through. So they're very common. Um, again, we're sort of at the basics still, so I like PyCharm for that, for the basics. The notebooks are really cool. You can do all sorts of things here. The NumPy library is awesome. You can create arrays really easily with them. And then they can fit arrays very easily for you as well. Multi-dimensional arrays, n-dimensional arrays we can do with NumPy. Right, we've done two-dimensional lists. Arrays are a little bit more basic. All sorts of fun things with NumPy. Um, logs of arrays, min, max, medians of like the standard deviation of array elements. Turns out there's a library for it. Right? We didn't have to compute standard deviation by hand. Who knew someone else had done this before, right? So you can get all this stuff done for you already. You can do a matrix product. You can cross multiply arrays here. So all the sorts of things we do in math class by hand, we can do with software like that, right? It just is going to go for us. It's really quick. Lots of fun things we can do with it. So we're just saying there's libraries out here you can use. Pandas, right? This idea of having data frames and using rows and columns. That's what pandas does for us, right? And then we can do some of that analysis. So pandas uses NumPy, right? NumPy. So I call it NumPy. I think it's NumPy. I think NumPy is funnier to say though. So you can make these data frames and you can do stuff with your data frames and it prints them out really easily for you and you can do fun stuff with them. Um, Matplotlib. This is my favorite one. We'll spend some time with Matplotlib because drawing pictures is huge. Now, anytime we talk about graphing, though, we have to talk about the idea that we should graph things responsibly, right? So you can lie with charts super easily here, right? So here's your US GDP from 2019 quarter two to 2019 quarter three. It's a small change, right? You could also graph it like this, where you change the starting value on the axis here. And you're like, look at this growth in GDP. Now, I'm going to bash on the administration because every administration does this every time. They exaggerate all of their numbers all the time and they cherry pick these things and say, look at how much growth we've had. And they can do that because they make these charts like this and they cherry pick, hey, from this quarter to this quarter or from this particular value to this particular value, look how big this number is. And yes, that's true, but it's not the whole truth, right? They're cherry picking here. So you got to be careful here. This is global temperature change here, right? You can show it this way, which is change, right? Versus the change relative to the average here versus change relative to the average kind of compressed, a lengthened vertical axis, right? This is 0.5, 1, 1.5. If we compress it and go, hey, all the way up to 5, the chart looks a lot smaller, right? Because we've compressed the axis. So you can present the data any way you want to, right? You can make it misleading or not. You can also super zoom in on it and compress it here. This is also made it mislead it and make it look bigger than it is, right? Look how fast this thing grows vertically, but we've super expanded the axis. So there's all sorts of different ways you can do it here with the way that you graph things. Temperature change and US GDP. Apparently, they're related. Related, you have to be careful with, right? Correlation does not mean causation. Hopefully, you've learned that in your stats class by now, right? Just because things are correlated does not mean they have a causal relationship. There's a super funny website for that. Funny correlations. There we go. U.S. spending on space, science, and technology, and suicides by hanging, strangulation, and suffocation. There's a correlation. I don't think there's a causation here. Number of people who've drowned by falling in a pool correlates with the films Nicolas Cage has appeared in, the number of films he's appeared in. The more films Nicolas Cage is in, the more people die by drowning and falling in a pool. That's a correlation, not a causation, right? Pretty sure he's not that bad of an actor, right? Per capita cheese consumption and number of people who died by becoming tangled in their bed sheets. Again, you can lie with your data. So we have an ethical responsibility to be truthful with our data, right? You don't want to lie with data. The divorce rate in Maine versus the per capita consumption of margarine. Apparently, consuming less margarine leads to less divorce in Maine, right? Age of Miss America and murder by steam, hot vapor, and hot objects have a correlation. Sure, right? This total revenue generated by arcades and computer science doctorates awarded in the US. Sure. All right. Anyway, so you can do funny things with data. So one of the cool things we can do is we can graph stuff with Matplotlib. So you can do any sort of cool plots here, and we use the library. So to add libraries, though, it takes a little bit here. So there's a new step because we're using stuff that didn't come with PyCharm. So I'm going to say this is a plotting project. So the first thing I want to do is I want to go and add the Matplotlib library. So I'm going to go to my settings here, and I'm going to go to my project, Python interpreter. Here I can add a package, right? And this is one of the things that why we have these virtual environments. We're going to add packages to the virtual environment, not to our main Python install. Now for Matplotlib, you'll be fine. But as you're adding packages and adding packages and adding packages and playing with things, if you add them all to that base Python install, weird stuff can happen if you rely on Python on your computer because you've added in other packages, and who knows if they actually work well together because there's 50 gazillion libraries out there, right? So this virtual environment keeps it safe. That's why we use them here. So I'm going to go say, hey, I want matplotlib. Here's matplotlib from matplotlib.org. This is probably the right one here, right? You got to be a little careful. There's all sorts of amazing stuff out here. Don't get the garbage ones, right? But sure, I'm going to install the package. It goes and thinks for a little bit here, goes out and gets it.
All of them will be original.
Hmm?
All of them will be original.
Uh, Based on the website usually, right? Yeah, there are people. This list of libraries is curated. Doesn't mean they're going to catch everything though. So we start getting into other issues where we start depending on other people's software. That gets to be a little scary at some point. Like we have to trust that it does the right thing. Because if they screwed up, then our stuff screws up now too, because we depended on their software. But it's basically everything is built. Okay. So I got the package, and now notice it installed all these other things, right? It uses NumPy, it uses all these other cool things from Matplotlib. So now I have a bunch of different packages. Great. Now I can go through and actually go and print something here. So most of the time we import it here. Why not? I'll just steal this one here. Sure. I don't actually want to save it here, but I'm just going to plot here. So NumPy lets me figure out this equally spaced array, right, with elements here. So I can quickly graph this here with NumPy. So a lot of times you'll see it's imported as PLT. So we haven't imported as stuff before, but this is a lot to type. So to save us some typing, we say it's as PLT, and then I can say PLT instead of matplotlib.pyplot dot whatever. I can say plot dot or PLT dot. That's all that is. It's just renaming here. So I'm gonna give this a run now. I actually get a cool little picture on my screen. Oh, I'm sorry, plot. Missed it. Plot dot show. Okay. So show will show the plot. Before it was just saving a file. Yay! So here's my plot. From -5 to +5, I've got a little straight axis and I've got a little curvy axis here, right? Whatever you want to plot here, you give it, here's my x times x times x, so that's my y equals x squared, and here's a y equals -4x minus 4. You can have different plots, right? So you just give it, here's what you want to plot, which is really nice. You don't always have to do the NumPy stuff, right? So if we wanted to avoid that for now, uh, let's just do a basic plot. So let's add some numbers here. So we'll say, I don't know, my values is, I don't know, values is a list, and for value in range, we'll do 100. Values dot append the value, and then we'll do plot dot plot values, right? And we give it a run. So here's values 1 to 100. Not a very interesting plot right now, right? I gave it, here's the values I'm plotting, right? If I wanted to do like the squared values, right? Value times value, right? We give it a quick quadratic, and now we'll see our quadratic curve, right? We're only going from 0, right? We're not going from the negative, so we don't get the whole curve here, or that sort of thing. So we can do some quick plots. Now, right? The x-axis, if we don't tell it, is just the index, right? The y-axis here is the value on that plot. So you can do all sorts of cool things, and you can set different values depending on how you want to do it here. There's lots of fun examples as we go in here. We're not going to do a whole lot of it. You can label them. You can play with them here. Uh, really fun things you can do to change your plots. Check out the library. You can do fun things. Any sort of graph you can imagine, you can plot with Matplotlib, right? They've got all sorts of amazing stuff here. Is it reference? They used to have a really nice. Yeah, here we go. Here's all the examples. So any one of these things you want here, you can go plot with this library and see how far down this goes. Like, oh my goodness, I don't even know what most of these are. I'll be honest. Like, I got no clue. A 3D quiver plot, 3D scatter. I'm sorry.
All these libraries.
Everyone uses Matplotlib. Yeah, super popular. So it's for graphing, right? If you want to give a visualization of your data, we're going to visualize it. Matplotlib is your quick go-to here. Yeah. And most of the time, people want graphs. Let's be honest. We love numbers. We like looking at numbers. We can understand numbers, but even us looking at like here's 100 values in a 2D array, it's an eyesore to look at that value. So plotting stuff is so much easier to represent and show data for people. And then for anyone who doesn't like numbers, don't even try and give them the table, right? Give them a picture because that will be so much easier. So um, any sort of graph you want, you can probably do with matplotlib. Right? I don't even know. Time series histogram, violin plot, multiple histograms side by side. Sure. So go through, find an example. They'll give you, so here's box plots here. Here's a box plot example. Go through and see. So if you haven't done Python before, you could probably make this work. There's actually some really cool math profs who go out and use Python for their lab exercises. So like, let me show you some quick graphs here. And they can get through it because it's not the worst language in the world, but having done some time with Python, you can hopefully understand this a little better, what's happening here. What is this random value here? What is going on? So that's why we look at it. So you can use the libraries. Okay. So one of the things we're going to look at here is this linear thinking, non-linear world. So our lab exercise, we're doing some graphs here. Here it is. So there's this article back in 2017. Wow, it's 2017 now, which is really neat. Um, Oftentimes we think of things linearly because that's how we think, but the world is non-linear, that's your clue for what's happening here. So let's take a look at this little example here. Uh, there we go. So we've got a company car fleet. We have SUVs that get 10 miles a gallon and sedans that get 20 miles a gallon. The fleet has equal numbers of each, and all of our cars drive about 10,000 miles a year. We have enough capital to replace one model with a more fuel-efficient vehicle to lower the operational cost and meet sustainability goals. Which is the better upgrade for us? To replace our SUVs that get 10 miles a gallon with SUVs that get 20 miles a gallon, or replace our sedans that get 20 miles a gallon with sedans that get 50 miles a gallon? Just off the top of your head, which one do you think is a better replacement here? Which is going to give us more fuel savings? B, to go from 20 to 50? Yeah, that's 2.5 times better, right? Rather than two times better? Sounds like it'd be better, right? Turns out though, the world is not linear. Right? It doesn't work like that. So let's go through. So let's spend a little bit of time here and look at this. So what I'm going to do then is see if we can't get these values out here. So this is we'll say this is my SUVs, right? Is a list. And now I'm going to have, this is my MPG, right? For MPG in range, we're going to start at 10 and we go up to say 20, right? Or 21, right? Because we're going to get all the way to 20 here. So this is my SUVs gallons used, right? So at 10 miles per gallon, right, my SUV's gallons used, I'm going to append in here. Let's calculate the 10,000 gallons, right, or 10,000 miles, right, divided by my MPG. That's how many gallons I use, right? This will tell me how many gallons I use when I get to 10 miles a gallon, 11 miles a gallon, 12 miles a gallon, 13 miles a gallon, on and on and on, right? So let's plot our SUV's gallons used. Let me go Y plots, X and Y labels. I forget. I'm just going to Google it here. There we go. Plot labels here. Thank you. X label is MPGs, and the Y label is gallons used. Right? Let's give it a run. So my MPGs. Oh, I don't want from 0 though. Shoot. Hang on. I don't want the values there. I plot set x-axis range. Plot a-axis. Is that it? Axis range. Plot. No. Setting the axis range. X limit. Is that what I want? X limit. Okay, so the X limit then is from 10, 20. That sound right? Let's see. Nope. Shoot. Oh, man. I want just to label it here. I want to limit it, sorry. Set the axis, plot axis. axis, range 10 to 21. I forget how this one works. I'm sorry. Let's see. Axis. Oh, man. All right. I gotta go look at a better example here. I'm sorry. It's in here somewhere. Let's see. Where did our. I just want a plot. Goodness gracious. Plot with different scales, maybe? Is that it? Tick parameters. Labels. Left and right scales. Ticker. No. Just want a regular plot. I'm sorry, I'm failing here. It's in here. It can do way too many things, and I get confused easy. Let's see. What's our labels? Dot plot, plot, x, y. Oh, there we go. Okay, so we just have to give it a different x and y, right? Is that it? Gives me my dotted line. All right, so I want the x-axis then to be, this is my MPGs, G's, equals range of 10 to 21. In MPGs, can I give it MPGs and gallons used? Hey, there we go. I figured it out. Sorry. It took a little while. All right. So to go from 10 to 20, we'll go from using 1,000 gallons to 500 gallons, right? So what we want to do here then is we want to also now graph how much we're saving then. So this will be our, uh, this is SUVs gallons saved is a list here. We'll take our SUVs gallons saved and we'll append in here. We know it's 1,000 gallons to start minus whatever this value is, right? That's how many gallons I've saved. And we also want to plot our gallons. Uh, let's just say gallons, right? dy plot my MPGs and my SUV's gallons saved. I didn't want debug. Shoot. Just a run. So my gallons saved goes from 0 gallons saved to 500 gallons saved, right? Based on this is how many gallons I'm getting, right? This is how many I'm using. Right? Now let's see if we can do this for my sedans. Right? So let's not plot the gallons used here. Right? Let's just show the gallons saved. Okay? And now let's take our range then from up to 51. Right? So this one we just want in range 10 to 21 for MPGs. And then we'll do our sedans. So sedans, gallons saved. Right? It's going to be a list here. And then for MPG in range, and we're going to go from 20 to 51 right here. Let's take our gallons saved for our sedans. Oh, did I not? Sedans gallons saved, append. Now, they don't start at 10,000, right? They start at 5,000, right? Because we're already getting 20 miles per gallon, right? So their base was 5,000, right? So we'll see how many we get here. Append, oh, I'm sorry, 5,000 minus 5,000, right? Here's the start minus the number used here, right? No, I'm sorry. This is 10,000 miles. My goodness, 10,000 miles. There we go. So 5,000 gallons to 500 gallons to start, minus the 10,000 miles we drive divided by our miles per gallon. Sedans. There we go. Sedans. So our sedans gallons saved. If we want to plot that, plot dot plot our MPGs and our sedans gallons saved. Shoot. They don't have the same size. That's right. Let's show the gallons. All right, we'll just wait on that. We'll show it to this one here then. Nope. Oh, okay, because they don't both fit. So I want to plot because so MPGs was off here. That's what it was. So MPGs should be from 20 to 51 for this one here if I'm doing sedans. So here's the gallons saved. For sedans, to go from 20 to 50, we only save 300 gallons of fuel, right? Because as we increase here, it's not a linear savings. The more miles per gallon you get, the less fuel you're saving, right? If we wanted to just go crazy here and say, hey, let's take this up to 100, to 100 miles per gallon, right? Let's do this in range MPGs. Range MPGs. Oh, it's just MPGs. That's right. It's not a range anymore. If we want to go up to 100, right? To go from 50 miles per gallon to 100 miles per gallon, we're only saving now 100 more gallons of fuel per vehicle per year, right? Because it's not linear, right? It's a curve here. The more miles per gallon you get, the less you save as you keep on increasing that value, right? That was the whole point of that. Okay. Super exciting, right? So again, plotting, it's a little tricky, right? There's a lot of pieces that go with it here, right? Making sure they match here with our labels and our size and whatnot. So, and looking at those errors and trying to figure out why they worked or why they didn't work here is important, right? So like X and Y must have the same first dimension, but I have shapes 80 and 11, right? My SUV's gallons saved doesn't have 80 entries. So it's not going to match here, right? So reading our errors here are useful. So if I want to say, let's take our SUV gallon used and then uh, let's take our gallon saved. It just depend on like a 0. So that should make it fit now. So it has the same values here. Oh, nope, it's got 10 more. Shoot. Let's go MPGs. Let's go from 10 to 100. Nope. Goodness. Do the same one here. Let's just calculate them both. Oh no, still off. Oh yeah, we don't want to do the 100 here. I'll just calculate them all. Can I expand this? All right, still not working quite right because we're getting negatives. So need some tweaking, right? Well, if you want to try and graph them both at the same time and make them look, we need the same axes as well. You can see where they collide. So lots of different things going on, but that's the idea. We can build out graphs, we can plot them, and they show pretty pictures here, which are really fun. That's the idea. So we'll do that as an exercise. We'll do that in lab, but I can't stay for lab. I'm sorry. So I'll post the assignment. If you want to work on it now, great. If you want to work on it later, we can work on it later. No big deal one way or the other. Okay. All right. So lots of fun with plotting. Takes a little bit of back and forth. That's all. All right. Awesome.